Okay. Board does not exist. Alright, so I was just implementing the search function last time. So let's do that. Let me just make sure that there's get pull, get log. The last commit is specify that search returns a number. Yep, checks out. Oh, I should specify that value contribution is negative because of the negamax, right? The negamax. We return negative value of the state, right? From the exactly the perspective. Okay, so we just have to implement this. That's like the heart of it, right? MCTS, the recursively defined search function. Okay, ls. Exactly. So like this right here, we have to. I have to implement. Okay. And then and returns value contribution. Now the whole negative thing, the whole negative sign, let's not worry about that right now. Okay. Right. So base case, if the state is already a terminal one, right? If it's terminal, if the game is over, then we return the negative. We just return the value, but we have to also negate it, right? So like if it's player one's turn, then that's like +1, but we return -1 because of the caller, player two. So like a win from player one is same as a loss from player two. It's point of view, right? So actually I'll add this line right here. Value contribution from the perspective of the player whose turn it is not. So not the MC node, right? Node dot game state dot whatever the thing's called is P1 turn, I think. Let me just see the game state definition. Is P1 turn? Oh yeah, I got it correct. Okay, good. So I'm in this. Okay, so right, yeah, okay, good. So now, let's see. The game is not ended. So then, now like calling this check in general seems a bit like wasteful each time because like to check if the game's over, we have to iterate through all the columns, all the rows, all the diags, forward diags, backward diags. So instead, we can just actually cache it in the MC node, right? So let's just do that. If the node dot is terminal, and then we just kind of like let's just cache it there. Let's assume that this exists. I'll implement it later. Then just return -1 times node dot. Let's just call it like game reward. Node dot. I'm gonna open up game state just to like see some naming conventions. So it's called game status. Game res. Let's just call it Actually, let's just add it in the. Wait, no, 39. So -1 times node dot. Wait, node dot. What should I call this? Node dot. Like it's kind of like crystallized value. Like it's kind of official. The game's over. So I feel like the word terminal should be used. So terminal value. I think that looks good. So now if this define like this thing right here, and then this thing right there, right? So let's just do that. Um, uh, this thing right here, right? Boolean, and then this dot is terminal equals to I mean, technically, is terminals kind of like implicit in the game state, right? um, hmm. Just pass it into the constructor and put it as a default parameter, I guess. Oops. And how do you do that again? TypeScript default parameter in constructor. Or string equals. Okay, equals and then the value. So then like the name type equals value. The name type equals value equals false by default. Is this optional or this is actually like default question mark string foo default new page default. Optional parameters function. JavaScript will take a variable number of arguments, and then we can model this as optional. So default is like an instance of an optional parameter. Parameters of a type number or undefined. Now in the body of f type number because any will be replaced. Okay, yeah, I think I think this is I think that's correct. Okay, yeah, that looks good. So is terminal is done, and then the other thing we have to do is terminal value, right? Why? Let's copy that. Terminal value is a number. Is there a way to like kind of chain these two together? Like if this exists, then if this is true, then this is populated. I don't know. I really don't know. Let's just terminal. Wait, what am I doing? I already. What? Terminal value, and it's a number. And let's just default it to 0, or draw, whatever, who cares? It's like JavaScript's default number is 0, that's a good default. This dot terminal value equals okay, that looks good. So if node is terminal, then and again, like we return -1 to make it I already explained that. Okay, let's see if this compiles. Okay, good, it compiled. Get status, get diff. Terminal boolean, terminal value number, constructor. Okay, I just added these terminal stuff. The whole point is like the whole point of all of that is just to like do this line right here, right? Terminal. Yeah, I should add a to do, right? Just to I should also add a to do right here in the 57, right? This line right here, to do implement the terminal check here. Game state dot called game status. Game status. Get game status. Check output of see if not ongoing. Okay, that looks good. Again, I'm just gonna treat this crate node as a black box for now. Okay, so if the node is terminal, we just kind of handle it like we're done, easy case. Then if the node is not visited, we add it in visited, and then we just kind of do that. Now this whole net.predict thing, like that's the responsibility of create node. Like it creates the node, uses the model's neural network to get the policy, and then presumably the value too. But then we don't really care about the value, to be honest. We just care about the actually no, we do. Yeah, we return the node and we return a number. So like this number is the value contribution, which is like this B right here, right? And then as for PFS, that is like implicit. That's like part of the node, because like the policy is used to create the edges, and the edges, remember, are a part of the node. So create node basically kind of does this. so like create node, right? But like we're assuming, right? So let's just assume, like, let's put in the search like really in like tree search you have like S, and like if you're like say you're doing LeetCode and you have like a tree node, like a binary tree, like tree node, which has a left child and a right child, which are both tree nodes, which could be either a tree node or they could be null. And this I'm talking about Java. I guess JavaScript is like kind of undefined versus null. I don't really know the intricacies about that. So like this thing right here is kind of like a if S equals null. But I can that's not my style. I actually don't like that. I prefer to like have a precondition that S is always not null. So like in this case, like when we're doing search or like the S is not really a state. I consider S more of a node in this function, right? It's a node. Like the node has the state inside it. Then like I'm gonna add a precondition here, a bit different from the way he's doing it. Precondition node is not null undefined. Actually, no, sorry. The node exists. That is, we have invoked this create node. Create node. We have invoked create node. Have invoked create node to create it. So it has been visited. Like the whole point is like if it's not visited, and like we kind of visit it. Okay. Basically, I'm kind of glossing over this right now by kind of like saying that like S will always be visited, so this never exists. Like we're pushing it down the road. Like when we actually do game dot next state to get this, then like that's when we have to kind of worry about it being terminal, right? Okay, so now we iterate through all the actions, but again, actions in our case is the edge. The edge is like has the move, it is the action. So then we iterate over our edges, and then we just find the one of the best UCB score, right? The Q score, like the exploitation, and then the exploration. Okay, so then let's just do that. So then we kind of like again, this MC node has a bunch of edges, so we just kind of iterate and choose the best edge to traverse, right? Okay, so then for what was that? No, redo that. Redo this. Undo that. Okay, let's just save this. This is a nice save point. And then for let edge of the node dot edges. So the edges and we're just iterating over this right now. So for the edge of that, and then let's actually let's just actually like kind of do this right here. Let best edge MC edge equals to and I believe like these edges are sorted by probability. Does that would matter? I don't know. I do not remember. But okay, edges. So best edge is it MC edge or undefined? No, I guess node.mc edges. So like these edges like is a list, right? Now, if it's not terminal, if it is not terminal, then the size of this must be there must always be some decisions to be made in the state. Like there is non-zero. It's greater than zero. There's at least some actions to be taken. So can never be the best edge. Like there's always some best edge. Let's just do node.edges 0. Now we can safely do that because like this is never going to give you a null pointer. Except it's never going to give you like a. It's never going to error out and like say that like the size is 0 because like this assumes the size is at least 1. And like if the size were 0 and this were to error, right? But then that means that it's contradiction. Like we would have already returned out of it. So for now, I'm just gonna make it the best. I'm just gonna kind of. I'm not gonna make the type. I'm not gonna like handle for undefined case like MC edge or undefined. It's gonna be MC edge. Okay, so then for the edges of like so for each edge, we have to get the Q score. Actually, let's just build that in. Like let's just actually build it in the edge. I think that's more kind of nice. And then how do you do this again? What's the syntax for that? We just kind of like write a method name. Actually, let's copy this line right here and dump it there. Get UCB score. get UCB score, and then that is the type of a number. We need a closing bracket too. Again, I'm gonna fill this in. Actually, there's no need for two. It's pretty obvious if the two do that. Get UCB score. Then let score number equals to edge dot get UCB score. Okay, like this. Let's see. So then, like this is the U, the score. Then if U is greater than max U, so again we kind of like set it as negative max U as negative infinity. JavaScript lowest number. Like what is that? Like 2 to the 64-bit signs, like 2 to the negative 2 to the okay, so negative, so like 2 to the 63 and then negative negate that. Number dot min value. Let's copy this. Number dot min value. So then let best score of edge number equals to this. Oh, I seem to have, let me wipe my screen. There's a bit of a smudge there. All right, quick coffee break. Okay, so then we get the score. Now, what if what happens? How they handle ties, right? Like, what if like it's strictly greater than, but what if it's a tie? Like, remember like in the initial network, like how like everything was an equal probability? Like, what do you do if it's a tie, right? Again, like we have like the like U is the UCB, it's the score, and then the A, like the best A is like the best action, the best edge. What if it's a tie? Do you really? I mean, is it really going? Maybe yeah, let's just be kind of very robust and handle ties too. So we can like randomly choose it. Instead of best edge, let's have it a list of that best edges in case it's a tie. So best edges. So then best score, let's call it best edge score. Best edge score. Okay, that looks good. If score is greater than or equal to the best edge score, then there's two other cases. If the, let's just kind of copy this. So if the score equals to that, or else something like this. Okay, and then we can delete these other lines. That looks good. So if the score equals to this, then we just kind of add the edge to our best edges. Then best edges dot push this edge, or else, and then at the end, remember we have to reset the score. Best edge score equals to this new score, and then we have to set it. The best edges, kind of like this, the initial thing, right? So best edges equals to edge. Let's initialize it. this look correct? So for each edge, we get its score, and then if the score is good enough to be a contender, then if it's a tie, we just kind of add it to the list of the best edges. But if it's so good, it's not, it's like strictly greater than, that is like this case right here, then we set it to the best. So it's like a singleton, it's a list with just one element in it, just like the edge itself, and then we set the score. Notice that we only set it in the greater than, because like if it's equal to, there's no point set. There's no like, I mean, this line can be kind of factored out, but it's kind of a no-op in this case. Okay, that looks good. So now, like, the only difference now is like there we just kind of have the action, right? Right there. But then here we have to actually like randomly like, let's just randomly select it. I know like, so okay, so now let edge to traverse, edge to take, MC edge equals to, and then we have to randomly choose it. Okay, I know. Let me check our commit. I mean, I know like I have some code. Like remember, like initially, like we kind of randomly sampled over the 7 columns. I know I had some code that did that. So let's look at that code. I'm gonna kind of copy it, integrating into game, maybe. So this map.floor random from 0 to 1 times that, and that gives you the dummy-bot move. The move is this thing is the column index. This is the whose turn it is and which column to select. So let's copy that here, right? Instead of gamestate.num columns, we want to do this best edges best oops, best edges. So instead of this, let's actually just copy this, paste it there. So in this thing here, let's just kind of delete that, and then let the just random best edges index number equals to this thing, right? Best edges dot, and then JavaScript array size length, right? Just dot length. Dot length. Okay, good. Wait, what? Fruits dot length equals 2. Wait, what the hell? 4, right? 1, 2, 3, 4. Sets or returns our elements into array banana and banana orange. Oh, so doing fruits dot length, we can kind of just like truncate it. So like in JavaScript, you have like array list dot. I mean Java, you have like a collection. You can have like an array list. You can have like dot clear. So dot length equals 0. Interesting. 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 Dot dot length. Len. How do you spell length? Length. Length. Actually, no. Let's just do that. Let's kind of copy this here, and then we can just kind of do that right there. Yeah, we can just delete this whole random thing. Just a placeholder. So right here, like we kind of take the best edges, and then we kind of like you iterate, and then we kind of use the this UCB score, and then we just kind of randomly sample, just to be robust and handle the tie break case. I think that's correct. Edge to take. Okay, so now before we move on, let's just actually actually implement this, right? So then UCB score, right? UCB score. We have to basically compute this right here, right? Okay. Q of S of A, right? This is like this right here. Ultimately comes from all these V's, like be it recursively or the first time, the base case or like the first time. So like, okay, let's just look at the initialization, QFSA to 0, right? Q of SA to S of A, right. Cause like it's kind of like looks like this, and then like kind of like all the stop not existing me, like so like when we initially call create node, we you can drag it here, so when the pop-up comes, I can still see it. So like here we kind of create the node, and then we kind of like do this, but then like these edges don't have any other nodes. There's no node, no node, no node. And the edge, like when we create the node, the neural network, like the value we get, the value contribution is just on this game state, but not on these. So like for all we know, like we don't know the value, so we just kind of set it 0. Now 0 means that it's a draw because -1 to 1, right? It's kind of like a perfect middle ground value, so we can safely use it. That's fine. So there's no qualms in using this Q score. So let's kind of first do this. The Q, that's a property of the edge, is it not? Yeah, Q score, Q. So then let just return the Q score plus. So that's the Q score, no problem there. I'm fully charged. Okay, let me disconnect that. Brighten the screen. Plus is cpuct. What is their cpuct value? Cpuct 1.0. That's a comment. Cpuct. What is the cpuct? Okay, let's just set let cpuct number equals to 1, whatever. Okay. Plus cpuct. Wait, what? Plus cpuct. CPUCT plus cpuct times. Oh, wait. Let's kind of give some space. Cpuct times what? Times PFSA, the probability. Again, this is initialized, like from create node. Like we already kind of did that. Yeah, okay. So that we just kind of do from here. The prob times. Let's delete all these white spaces. Prob. So probability times JavaScript math.square root. Square root. Yep, math.square root. So math.square root of the number of times the parent, right? Like just clear that out just to see the commits. Okay. Okay, so square root of the sum of NFS, right? Like kind of like this right here, right? Now, like, I think I mentioned this, like, rather than like kind of summing it, we can just like we already store it on the state itself. Like we already store it like right here, num visits. Because like I already mentioned this last time. Like if we have, let's just duplicate this, create a new one. I know I mentioned this. Accept whatever. I'll accept you. Like again, like we have like this thing right here. Like we kind of visit like, let's say like there's like 3 actions we can take. Like this one gives us a value of like 4. Or no, we visited this edge 4 times. This one 2 and this one 1. Then like that means like we visited this node a total of like 7 times. We kind of store these on there. So like we just kind of use that number. Now to make sure that these align, like there's no off by 1 errors. I'm pretty sure that's correct. Or I'm like 42. Oh wait, no, then I can't do it. Because this edge doesn't really know like the node. Okay, so let's actually get rid of this function then. Yeah, so these are just kind of like POJOs, plain old Java objects. But yeah, POJOS instead of POJSO, POJSO, I don't know, whatever. So then we can kind of do that there. Like we have to, like wherever we can invoking the function in the actual search, we have to actually like do this, right? Oops. So score is the score instead of edge.ucb score, the edge.q score plus like that, right? So the edge.q score plus the cpuck times the edge.prob times mat.square root of, and then instead of the like now like we kind of have access to the actual node itself. So the node I'm caught between like the history of the undo and redo. Let's undo everything. I'm a bit lost what was going on. So from this to that, there, just save that. So the score is the edge, and you have to kind of copy that, right? So the edge is Q score times the cpucks times the edge probability times square root, and then now rather than like doing like the whole like summing everything, we can just kind of like use the number there. And that is the node, right? Like this node, we're exploring it. Like that node's all its children dot num visits, right? Visits. So that's the numerator. That is the numerator. And denominator, again, this could be 0, so you have to add a +1, I'm guessing. Like that kind of, that has a nice thing of like never dividing by 0. Divided by something, which is 1 plus, and this time the edge dot num visits. I feel that's correct. Am I missing something? Oh, just to get rid of that line right there. So then let's look. Okay, so then the edges Q score. So now, how do we know that node.num visits like equals the sum of everything? Let's consider some base cases. So like when we first call create node, like when we first do this thing right here, right? Then we set like the NFSFA to the edges as kind of 0, and then like for all the A, and then like for all the yeah. So okay, yeah, okay, exactly. So in the search, what we have to do is actually increment that. So then um So only after we use the value can increment it, right? Like we're searching this thing. So the moment we search it, we could increment it. Like what I was first thinking of doing right here, right, is something like the node dot num visits visits plus plus, right? But then we can't increment it here. We actually have to increment it like after we use it, because we like the point is that like the node's visits and the like this both like MC edge and MC node both have like known visits, and they have to kind of like visiting a node means we have to kind of like visit like we need all these num visits to sum up to that. So whenever we kind of, it's the same thing as value contribution, similar concepts, how like these from like edges propagate up. So like kind of like that. So like only after we kind of explore the edge can we do it. So we should only do that at the end, not the very start. So the whole point is that like this thing right here, let's delete this line. And only after we recurse can we do that. This line has to be after we recurse, just like the value contrib also bubbles up. That's a good save point. Edge to take, and then we have to kind of recurse it, right? Okay. So now I have to like take the next case, and then like we just kind of like recurse. So then here, remember how like this thing right here, the S is not visited. So I'm like, it's like kind of like the whole like leak code like tree node did df depth first search on the DFS on a tree node. Like we only like oftentimes you have a thing where like you have a tree node left child right child, and like only if the left child is null or not, only if it's not null do we recursively do it. But then if it is null, so if instead of like this whole check right here, and as a base case, we're kind of preconditioning it. So we have to kind of we have to like now it's the time to actually kind of handle this like kind of like this null check we're gonna handle right now. So like that's kind of what we have to do. And then so like if the I'll write the code. If the edge to take dot I have it here. Node is undefined. Exactly this one right here. Num visits equals 0. So like if the edge to take dot so if the edge to take dot node, I think JavaScript we can somehow do that. Else. Okay, so like this is where like the kind of so like this is where I'm actually using a JS feature. So like if this node, right? Because like if the node visits is 0, that means the node is undefined. And undefined kind of evaluates to false. So let's kind of put a comment here. No, edge has been visited before. It points to a and it's like points to a created like kind of create node created point. Anyways, edge has been. So the point is that like the point is that that's not. The point is we can recurse. Search, and then like we can kind of like we don't actually have to compute the next state. We can just kind of like we already cached it in there, right? Like we already have the game state in the node, and the node's not null. Like we don't actually have to like advance the state. We have to do it in the else case, right? So like here, search, and then like the edge to take dot node. So like here we have to kind of it's like we recurse on the node and the model. Just kind of do the node and the model, Oh, we have to consider the return type too, right? Yeah, let's just do that here. Let value contribution number equal to 0, whatever. Let's just return this actually. Let's return negative. Let's return but merit to take it -1 times that. So then here, right, at 67, line 67, this thing, oops, shift paste equals that. Exactly. We're just kind of like, we're just recursively doing it. And then, right, to apply the value contrib to our stats. Basically just like these lines right here to kind of apply. Yeah, exactly. NFS, wait, the edge visits. Okay, I'll just do that right there. They're there too. The like after we kind of recursively do whatever, like the point is that like we have the edge to take, and then after like this whole thing, we take the edge, either recursively explore or like first time explore. And we're like we could do the create node, and then like here the edge to take dot num visits plus plus. Delete that comment. Delete this. Actually, let's keep that comment there. So this one is an easy case where we just kind of recursively do it, where we just kind of simply recursively do it. And in this case here, we have to actually like kind of do the create node. So that's the fun stuff. Like basically like like if you kind of like, so it's like kind of like, let's say like here, like we take this action, like we chose this as the edge to take, and this already exists. Then we kind of recursively do it, and we keep doing it until like, let's say that we decide to like take this edge right here, but then it has no, like it's kind of like the leaf. Like we've kind of like hit a point where like we have not yet explored this edge yet. Its num visits is 0. Like this one we've explored at least, like we must have explored, because why else would we have the node, right? This node right here. So like here we don't actually have it, so you have to actually advance the state. So here's where we actually need like, so like comment. Advance the game state. Like I guess like clone it. I think. Clone it. So we can't like use the same thing. We have to clone it. Clone it, I think. Then apply. So you have to define a function clone if it doesn't exist. I don't think it exists. But apply the move to it. Yeah, deep clone is very important. We don't want to like, it has to be a deep clone. Yeah, I'll deep clone it. Deep, like we don't want the nodes to like share, like work on this. It has to be immutable. Like the node's game state must be immutable. Like future nodes, like they have to point, each node has to have their own game state. Like, and changes to one should not affect changes to the other. Deep clone the node dot game state, I think. I don't think I know it. Deep clone, then apply a move to it, then invoke the this thing right here, create node on the game state. Create node. That's kind of like the what our job is. It's kind of to do that. Okay, so then do you have a deep clone thing right here? I don't think we do. So well, nice. We have the file opened up. Game status, which just kind of returns like whether we're finished or not. Like, returns the game status, ongoing, player 1-1, whatever. Apply move. Okay, so we have apply move, and I see that we have get legal moves. Get legal moves. Wait, what? Oh, so this comment right here kind of, Vim thinks that, I mean, we want this to match. Let's just delete this comment then. So now like this bracket here matches the class. Okay, so now we have to kind of create a new thing, which is dot clone. Now should clone be a like? I think it should be a static actually. Like get game status, or should it be dynamic? I mean, should it be instant? Should it be like static function or not? No, whatever. We can just do the clone, which returns a new game state. Okay, let's look at the constructor for game state again. Constructor just. Okay, so what does the constructor do? It just kind of, the whole point, like the whole meat of it is just like this thing right here. It's to create a bunch of like these rows, like row times column, 6x7 2D array of cells. So you just have to kind of like hard copy the cell. That's it. Now these cells are like an enum, so they're pretty much constant. So like even if they point to the same cell, like that's pretty much a primitive. So I guess like it's okay to like kind of like we can't point the cells. Like we can't like say like the new object dot cells equals this dot cells. Instead, we have to kind of like do this similar thing right here, right? Something like that. Okay. Let games let's call it copy game state equals to just new game state like that, and then we just kind of return the copy. That's kind of like the idea. Okay. Run rows, cells. So then for each row, okay, sure, well, why not? And then for each and this dot cells, no, so it's going to be copy dot cells, new row. But instead of doing this cell awake, we have to kind of replace this to instead be a. So instead of doing a vacant cell, what we have to do is kind of like this dot cells dot r dot c. Slide like that, right? Something like this, I think. Okay, so like we're iterating over the rows, then we're iterating over the columns, and then basically we just kind of like, so let's say R0, the first row. Then we're kind of giving a copy ultimately a new first row. Zero means zero index, so first row. And then so again, this R is always zero, so it's iterating over like this dot cells R, like this whole thing is first row. So iterating all of that, and we're just kind of like doing it. So like now like the cells, like by doing new game state, we're creating a whole new like object. Like the object's like cells is different. Because again, like this dot cells is a whole new thing. Like the pointers are now like they do point to different like cells is different. But the actual stuff, like it's just an enum, so like we can like it's a constant, it's immutable. So I think that's fine. Like we don't have to actually like we don't need to worry about like we can just like directly kind of steal the enum. Like like there's no need to like kind of create a new enum, I think. We can just kind of copy that. Maybe I should kind of put a like note my um like okay, I think this is fine. I don't see any issue with this. just, I think this is fine. Clone. So we create a new copy, just a new game state, and then we, game state. Okay, we're creating. Okay, that looks fine to me. Okay. So let's call this next game state. Like it's kind of like the next state SP. SP stands for S prime, right? Like this kind of like SA and then S prime, or that's what I think SP stands for. S and then tick S prime. So next game state equals to first we just clone it, just our node dot game state dot clone, which we just defined, and then we have to apply the move, right? Next, huh? Dot called apply move apply move dot apply move the move, right? And the move is part of the edge to take. Edge to take dot move, right? If you look at the edges, the edge has the move. Okay, so now that we have like the move, then what? So now we have, so now like after doing these two things, actually we can just chain it, right? Let's just chain it. Or no, okay, so that's the game state, then we apply the move to it, so now it becomes a next game state. Okay, that looks good. So now that we have the next game state, we have to actually like kind of like do a search. We have to kind of do this in it. And that's kind of like the create node. Okay, so like kind of this whole thing is like create node for the first time. So create node takes in game state and model and returns MC node number. Okay. So then create node result res. Let's copy the constructor for that. Just to let's keep it in a comment. Equals to create. Looks like we're creating the node on the next game state. Next game state, and we kind of reuse the model. Great. Okay, that looks good. So then this value contribution, right? The value contribution equals to the create this whole thing right here 1 to get the number, right? This thing returns the value contribution. That's the value contribution. Okay, that's good. Kind of like matching that. Like we actually like create node, like kind of will create the node, and it will like invoke the neural network on it. It'll basically like just kind of invoke the network on the state. It'll return the value. It'll also return wait, what? Policy for the node. So basically, kind of like when we use the policy to create the edges. Exactly. That is correct. Like by using the policy to create the edges, like kind of does like PFS, which is basically like doing this, like this whole thing right here, like this equals this. Like it's like a a tuple like kind of like unboxing, right? Like kind of just same thing here, like 0 and 1, where it's kind of like the P comma V like node kind of has the edges, which kind of have the weights, the prob weights in them. So like it's kind of like similar thing. So then the actual node, right? So we have a whole like we have like this whole like this whole like kind of this whole kind of tree going on, right? So let's actually like kind of do that there. Like right now, the edge to take that node is null. So now what we have to do is actually have to kind of like make it not null, not undefined, right? So this right here, go there, paste that there, equals to this thing but 0, the actual node itself. Perfect. I think that's it. I guess this whole 1 before 0, let's just swap the order to make it look more. And that looks good. I feel like I've done enough work for now. I feel this is pretty good. I think this is. Well, no, I have to actually invoke the value contribution. I have to use a restroom really badly. But I kind of want to finish. Actually, let me use the restroom, then I guess maybe this crate note I'll do next time. Now I'll just do the to do and then make sure it compiles and then like do that next time. Actually, no, it can't compile because like crate node hasn't been implemented yet. Oh, um, well, let me use the restroom. Okay, right. Where was I? Okay. So right now, crate node is doing a lot of heavy lifting. So to make this compile, like this has to actually like we have to uncomment this part and like actually like have it return like the node and the number, right? Okay. I know I did a lot of stuff already. Um, I'm starting to feel tired. Let's see. Okay, so then everything right now is contingent on create node. Okay, so once we do all this, yeah, let's just finish this function, then like treat this as a black box and then do that. So I do want this to compile. Or well, maybe next time, I don't know. I can just like kind of create a stub, just stub it out, like create some dummy, like kind of like how I used to return 0 here. Okay, so now what do we do? Let's kind of review here. So like so far, we kind of looked over all, that's the base case, terminal case, if it's terminal or not. Again, like to do implement terminal stuff in here. So we pretend that these two things are properly set. So if it's not terminal, then we iterate over all our edges. We look at the UCB scores, the Q score plus like the edges store the statistics, number of visits, and like the Q score so far, right? And then so this is node.normal, just the edge, and then +1. Okay, yeah, that looks good. So like we kind of use this UCB score, and then we just kind of like iterate all the edges. Then we kind of choose the best edges, kind of by iterating over them. If we kind of improve them, okay, sure, that's good. So now I have best edges. We randomly sample, like completely randomly for tie breaks. We just randomly break ties, like randomly choose any of the best edges. So now we've chosen the edge we're going to take by random. We should take this. Okay, so now we know which edge to take. And then if we've already traversed this edge before, if it's not our first time, that means we already have like its node. The edge points to a node that we've created, and we just recursively explore that, and we get the value contribution. Again, by this whole negative thing, kind of the value contribution is from our node's perspective. Like each node has a game state whose turn it is. Like when we do apply move, right? Like if you have, like, I'm in line 72. If we do apply move, then like what we do is like we do this dot is P1 turn equals to not this dot P1's turn. Like it toggles, like it toggles the turn. So like I talked about this case. We just recursively do that, right? I should take dot node. So I should take dot node like again. So like we chose like which edge we want to take, like which action is the most kind of promise. The edge to take is like the one the best UCB score, like which one we decide to explore in this iteration of search, in this kind of Monte Carlo simulation, search simulation. Then, so like we've chosen the edge. Now, if we've already visited the edge before, we just kind of recurse on it, and like we kind of bubble it up here, which I'll do. Or else, this is the kind of the more interesting, like the base case part. The base case that was kind of implemented like right here, like we're kind of handling that in this else case. What we do is we have to actually like apply the move and like so like game state.clone. So like we get a deep copy, like we get a copy of our game state, right? Our game state, our node's game state. And then like we need to apply the move, but we want to like apply it. Like we want to like duplicate it. We don't want it to like point to the same cells. Then we apply the move. And apply the move, as we just saw here, it swaps the turn. So now like the turn is from the perspective of the the opposite perspective of this node. Like if this node's for player one, like node dot game state dot is player one turn is true, then now like this game state's player one turn would be false. It's the other player's turn. So apply the move has the side effect of also like swapping the turns. And then what we do is we like kind of, so again, like we have never visited this edge. In this else case, we've never visited the edge. So now we actually visit it for the first time. So like right now, the edge kind of looks like this. Like we choose this edge, but we've actually never visited it. So we're going to like kind of connect the dots and create a new node with empty edges. That's kind of the idea. We've never visited it before. Like we have never visited it yet. And once we're done visiting, then we kind of get this looking thing. But we haven't visited it yet, right? So we want to create a new thing. So we create the node, and then we create the node, which kind of returns like this new. It returns the actual kind of circle object we just did, and it also returns like the number, right, which we want to bubble off. So value contribution gets that number. Again, I think I talked about this last time, like alternate value contribution. And then so the whole point is like in both the cases, we actually like kind of like in this thing, the graph exists. Like we have the pointer to the node from the edge. In this one, we actually like do the assignment. Like so like next time we traverse this edge to take, this edge to take that node will not be undefined anymore. It'll be something and we'll kind of recursively do it. So like only once do we actually have to like create it. Like we create the node once, and then now that it exists, all subsequent times we take the edge, we always do that. Right? Right. And then we do all the bookkeeping here for the gnome visits. Like whenever like for all the edges, like after we kind of like this whole thing is like exploring the edge to take. Now that this whole thing is taken, that means we've kind of like taking the edge basically means that like we just kind of either recurse or like we kind of do the whole thing. But the whole point is after we take the edge, we get the value contribution from taking the edge. And now we have to actually apply and bubble it up. Like this one, we have recursively it's recursively bubbling up this one first time neural network spits it out, and now we have to actually apply it, right? So now to our stats, right? So then what stats we have to apply to? Well, simply like we do edge to take gnome visit. It's edge to take, right? Edge to take. So edge, because edge to take keeps track of its Q score. Now I have to kind of do that, right? So let's see how it's done here. Right? QFSA. NFSA plus equals 1 is done right there. And then now we have to kind of apply this there. I think, well, they do QFSA first. Okay, yeah, that's a good idea. Let's do that there. So edge to take. And it's Q score, right? Dot, what's that called? Like edge dot Q score equals, and then we have to like kind of Q score. I don't like this. Like if I were implementing a running average, I'd actually want to like store the total. And when I okay, yeah, let's just change it actually. Let us change it. Sorry about that. Let's do 39GG. Get Q score number equals to how do I define functions again? Sorry about that. I don't really know TypeScript well. Just function name like this. The name. Let's copy that there. So in return, let's call this a sum Q score. Q score sum. Q score sum. Q score sum divided by this dot. Don't forget the this dots. Num visits. So that's get Q score. So when we use this, right? So instead of that in lines 58, right? Like this line right here. Instead of that would be a get Q score. Exactly. So now this Q score sum, right? So edge to take dot Q score sum, and that would be we increment that, right? The Q-score sum, we increment by the new V. That's it. We're just instead of like kind of recomputing the average each time, we just kind of let's just store only the sum. That's it. So like we kind of like now we only kind of get the Q score on demand. Like whenever we traverse it, like whenever we kind of like decide to take the edge, then only like what am I saying? The point is that like when we're visiting a node, we have to kind of visit all the edges, but we only visit that node like if it is a promising, if it's like a very bad node from the perspective like the point is like as we do MCTS Monte Carlo tree search, like certain nodes get visited more than others. So like some actions are more, some edges are more promising. So like we kind of take those promising happy paths more often, and some kind of undesirable. Like we don't care about exploring some regions. We don't really like explore them too many times, right? It's kind of like the intuition behind MCTS. So like those are not really explored. So like we don't really need to like get the cues. Wait, why am I? Wait, how does this relate to anything? I mean, maybe there's like some precision lost by doing this multiplication, like a float and then an integer. Wait, anyways, the point is, I'm just kind of doing this on demand. That's it. I'm storing the actual sum. So edge to take dot q score sum plus equals what? The value contribution, right? Simple, just that. And am I done? Is this it? Could this finally be finished? So I think I'm done. Like, and this should be general to any game, like not just Connect 4. Everything's in terms of like the edges, like the nodes, and then, like there's no Connect 4 specific code in this at all. Okay, so I think I'm done. Just all we have to do is implement create node. Like, that's it. Oh, let's remove this to-do comment. We advance the game state, and then we apply the move to it. Wait, advance the game state and apply move are the same thing. But the whole point is that these two lines kind of handle this to get to do and create node. Okay, I think I'm done with search. Well, this is a lot of work. Like, this is a pretty hefty function. And now just create node, right? So now the whole thing is to actually create the node. So let's take this all here and then bring it to life. So create node, game state, model, node, number. So like we already like we're actually like here's where we finally like search takes in the model, but then the whole point is that search the model it passes it on right here. That's the only place it's used, I believe. The whole point is we have to kind of pass in the model all the way into create node, bubble it all the way down until we're actually kind of using it here, right? The only time the model as a net is actually used is this line right here. That's it. Okay, so now we have to kind of like invoke it. And then I think it's net. It's either bot.ts or net. I think it's net.ts. So let's put that there. The ts net.ts, right? Convert game state to model input, but I think that's kind of like more like a private function that get policy and value. So this is like the key thing right here, right? Get policy and value. And that's exported, right? But if we look at 62, this thing. Actually, let's just kind of like invoke the usage, right? In a bot.ts, I think. Right here. Get policy. So let's kind of copy this, right? Let's copy the declaration. This is MCTS, right? Okay, good. Get policy and value. That's good from the net. And then what? Copy this line, right? Policy and value, game state, model. Something like that. policy. Let's get policy and value. No, but we want both. We don't want just like the zero. Zero is the policy. We want the value too, because that'll be passed in here, right? We have to also do the to-do thing here. Yeah, let's actually first do the to-do. Well, whatever. Policy and value. Let's call this policy and value. Value. What's the return type? Policy and value. Policy number. Policy number equals to that. Okay, so then so now let game let or if the game state game status is not equal to the ongoing, right? What is that called? Game status dot ongoing dot ongoing. So game state is terminal is terminal. Game is over. Game is over. Game state is over. Let let terminal node MC node equals to a new, whatever, let's just fill that in later. Return terminal node. This returns two things. Terminal node. Terminal node dot, and like I think that's stored somewhere there. Terminal value. What's the constructor? Okay, so then new MC node. All cross. And first to the game state. To be honest, none of these parameters really matter except for is terminal and terminal value. Like, that's all that matters. Whatever. Pass in the game state. Fair enough. Game state, and then edges, again, like, it's an empty list because, like, it's terminal. There's nothing more to be done. Is terminal is true, and then terminal value. Just gonna copy that there, terminal value. Take that there. Like that. But, oops. Goes to 0. And then, if, the, Actually, let's do it right here, right? Nested ternary condition. Switch. Yeah. JavaScript. Or no, type. Enum. This code works. Okay. Switch. Switch. Parentheses. Games. Just quit this. Or actually, no. What? Grep. Cursively, and then let's do C5 maybe. Oh, no. Wait, no, maybe not recursively. Okay, so in game.ts we have like switch game game status. And how do I do the line? I think it's line numbers, and it's like, what's the flag for numbers? N. Okay, so in game.ts 59. It's already there. 59. Okay, exactly. So we know it's not ongoing, right? So we can kind of delete that. Game status.1, then terminal value equals to so if player 1 won, then depends on whose turn it is, right? State dot is P1. Game state dot is P1 turn, that's correct. So is P1 turn. So if it's player 1's turn and player 1 won, that is +1. Or else -1, right? Or else if it's not player 1's turn, that means it's player 2's turn. But if player 1 won, that means in the perspective of the other one, it'd be -1. Kind of same thing here, except we swap them, right? Oops. So here, number 2, right? But this is for number 1. So like if the number 2 was the victor, but then from number 1's perspective, that means -1, or else it's 1. And if it is drawn, well, that's pretty straightforward. We just set it to 0. And then what we do is we just create a new thing with the game state, sure, empty, its terminal, and the value. Okay, so then this is the base case right there. If it's terminal, that's quite straightforward. So this to-do is now finished. And now that we're here, that means it is ongoing. So now I have to actually use the network, right? So then what we do is we get the policy and value, like we take in the game state, and we convert it to like this get policy and value is what the net does, right? Actually, just like if you kind of look here, right, the net get policy and value, it converts it into the tensor for they can just pass it into the network. Also does some filtering too. A new policy also does sorting. Filters that illegal. Actually, I want to change this. I remember like I was being a bit annoyed with this arbitrary 0.1001. Let's actually do that right there. Let's actually delete this. I don't like this. This seems like a very ad hoc kind of like off the cuff random nonsense. Let's actually delete that, right? And then now like I was worried about this being 0, right? But now if the move probability, okay. And now the question is what if this is 0? So let's do that as in like in an else case. So then, okay, we have legal moves and legal moves with probs, and then we're kind of we're looking at that. So there's two cases: either some probability is not equal to 0, or it is. Okay. If some prob is not equal to 0, else, and this case right here is if it's not equal to 0, right? Because it's not equal to 0, then we can divide it. And if it is equal to 0, that means then what? Then let's just like uniformly sample it, right? Then then let prob number equal to just just uniform, right? So 1 divided by legal moves dot length, something like that. Like if there's like 3 moves that are legal, each with probability 0, right? If they're each probability 0, then like let's just give them all 33.3333 infinite chance. So like 1 divided by 3 is 33 in infinite degrees. Then like this thing right here. What? Wait, why are we doing this again? Legals and props? How does that populate it? It's a pair, it's like a policy. Move, and then the probability of it, it's empty, and then for move. So the move is size k. Oh, here it is. That's why. That is why. Move and prob. Policy data, move column index. Okay, legal moves just gives you legal moves. And then we're joining on this thing on policy data to get the actual probability, and then we're okay. Right. I think that makes sense. Okay, that was good. Just refreshing my knowledge on that. We do something similar, except now rather than this thing right here, what we do is just set it to prob. Avoid the 0. Prob. What? I'm so confused. Prob. Right? Like rather than do this, because like this is the case where it's equal to 0. Here we just kind of do it uniform. Just to like be super sure that this is not 0. I mean, if it is 0, we don't want to divide by 0. I don't like that 0.001 nonsense I did earlier. Okay, so this thing converts to that, and that's from a long time ago. Or like we could do the whole like it's nice that we can treat this as a black box. And how does this work? I mean, do I really care? I mean, I've already is it crystallized yet? Current player cells. How do we determine like that's the game state is player one turn? Where's that used? Turn. Oh, this is empty. Yep, is player one turn. There's some switch, like there's some like condition on that swap. Okay, that looks good. So this will return like filter. It'll return the actual policy and value. Like perfect. That's good. And then bot. Okay, so we have so back to create node. We have policy and value, and then from that we want to like again the whole goal is to do this, like create something like that. The empty thing. Wait, what? We want to create like this thing right here, a new node, and then a bunch of edges that point to nothing. That is that's the objective that we want to do. Okay, I'm feeling tired. I just want to wrap this up. Okay, you got policy and value. Okay. So we have to, so like we want to create a node, and we want to create the number. So like the value is this number, the value contribution. Do we have to negate it? Like, do we have to like do this like negative v? Okay, let's see how this function is used. Create node is used right here. Create node res, and that's the value contribution. So yeah, we have to negate this. Like we'd have to like return MC node, and then policy and value 1, but negative, negate that, like that. Now the only thing left is to actually populate MC node. Let's call it node. Let node. So like this. Oh. So how do we create the node, right? We have to use policy and value to create the node. So we have to use the model neural net on the game state to get the policy to create the edges, and then return MC node, also value contribution. So value contribution. Because again, like, why is this a value contribution? Like this get the policy of the value, like the neural network's estimate of this, which is the contribution. Again, contribution I mentioned last stream or even two like a whole bunch of times. That's like gets bubbled up. It's like what the state returns is a contribution, not the value of the state, but rather like after doing the playout or neural network in this case and like propagating it up. Okay, so in this node, the constructor is the game state. Let's just do it here. Let's kind of copy that there, right? Like something like this, right? Wait, okay, let's kind of do that there. Replace this with that. In this case, the terminal value is false. Actually, we don't have to specify. It's optional. It's a default. So I do this. The game state, which is right here, and then the list of MC edges. So now let edges MC edge list. Wait, -1 of 7. Goes to that. Okay, so now I have to kind of create that. policy equal to so this is like kind of unwrap this here. Value number equal to, let's just kind of use that there. Okay. So from the policy, we can build up the edges, right? So for policy that moves the probabilities, you know, sorry about that. Okay, so we're on line 110. Of this for move and prob for a let move and prob of that. Okay, then it should be like move equals to 0. That would be F1. Unmarshal this. Okay, so we have the move and the prob. Now I want to create a new edge and push it into edges. That's the goal. Kind of copy the constructor there. I'll just move and prob. Oh, that is the constructor. MC edge, just a new move and a new prob. Okay. Edges dot push new MC edge move prob. And that's it. Or am I finally done? Edges dot push new move prob. Okay, so then create node. Game state, if it's terminal, so if it's not ongoing, that means it's terminal, so then we kind of get the value. Okay, we kind of already talked, okay, so that's terminal node. This whole thing is a dummy object. We only care about like this being true in the terminal value, because that's how we actually like use it in the terminal. If it's terminal, we only care about the terminal value, and then we return, that's it. So yeah, this whole thing checks out. Then if it's not terminal, that means it's ongoing. The game status is ongoing. Then we can like kind of plug it into a neural network and get a policy and a value. So the value gives your estimate that we propagate up and we return the negation of. And then the policy, right, has the moves and probabilities only for legal moves. Those are only edges we care about, those that are legal. And that's it. And then it's new MC edge, so like the MC edges are kind of like they don't point to anything, like they have no nodes attached, right? Yep, like this the node is undefined because like initially num is 0 and the node is undefined. I think that's it. Let's see if that runs or compiles. Okay, of course there are errors. Line 74 cannot assign to game state because it is an import. What? Import game state. Dot clone. Clone returns a game state. What am I missing here? Oh, just let. Oh, it's thinking game state equals. Okay, I see the problem. Yeah, let state. Okay, now let's run it, see how many errors we have. Should just clear everything. Too much clutter. Okay. How many errors now? 8 errors. Previously, how many errors? 11. Okay, 3 errors done. Line 76. Another let nonsense. 76. Okay, 4 errors. That's good. Cannot find this. Is it a missing import maybe? What is this? I want to copy the import statement, right? This line right here. I guess 1 error. Oh, it's a function. It was error line 90. Wait. Yeah, okay. I should just cache it. I should cache it instead of calling it twice. Like, I'm using it here and here. I should just like kind of get the game status. Okay, that looks better. Make sure it compiles. Of course, dumb typo. Okay, that looks good. Get status. Clear. Get diff. Okay, so what did I do? I added a clone. I added game status, import, and then I'm using the neural networks, the the function in this net utility class that just takes the model, the neural network, and it just kind of applies it to game state by converting the game state into a tensor, right? Like the two image stacks, and then like puts it, like calls the predict method, and actually gets the passing value. I believe it must be synchronous. I mean, I know I use it in the game itself. And then, yeah, like things like dot data sync or whatever. It's not like async, it's synchronous. We get the passing value. Could take a long time, who knows? Depends on how complicated the network is. Then cpuct, MC node. We just add some terminal things so that like the whole idea behind that is to like, we don't want to like every single time like check if it's ended. That could be pretty wasteful in case like it's difficult. Like in BumperCoins, it's easy. You just iterate all the coins, king, see if the health is 0. But in like for this one, it's iterate all the rows, the columns, the front diags, the backward diagonals. It could just be hassle. So like cache it onto the actual like node itself. That's why I'm sticking the terminals. So that's pretty straightforward. We have some default. By default, it's always going to be false, and then just the number doesn't even matter if it's false because it's never used. It's only consumed if it's like true. So whatever, we just kind of just conventional this dot whatever equals itself passed in. Q score sum rather than store the score like they're doing here, because like here we're kind of like taking the score, multiplying by number, and then kind of adding it and then dividing it again. Like just store the running total instead. That makes more sense to me. Just kind of store the sum of all the kind of V contributions, and then like to get the Q score, we just kind of take the sum and then we just divide by num visits. And what if this is 0? Oh yeah, what if this is num visits to 0? Okay, well let's say num is 0. How does this handle it? If this num visits to 0, then the denominator is 1. Wait, no, it's right here. Initialize QFSFA and NFSFA to 0 for all A. So initially it's 0. Then when we first do it, okay, let's just say that like we call search for the very first time, right? Like the very first time. That means like it's like do search, right? Do search. Wait, what? Do MCTS, I think. Right. Like we're calling for the very first time. We just create the node, then we just call search for the very first time. So create node, but we'll like kind of so like create node would just kind of wait. So create node, what would it do? Game state if it's ongoing. So like we kind of create these, and then like we create the new edges, and then the Q sum whatever would be 0, right? This would just be by default 0. And then so like initially it's 0. So like our first iteration, the very first time we create it, would just be like we start off. It kind of looks like that. We just kind of call it for the first time, right? Like we just created a root, and that's how it looks like. This is our root. It just kind of looks like that. It's like each edge point does not point to anything. Like there is nothing in each edge. Each edge, 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 Edgar, edge, and then like the first time we kind of like call search on this, then like that would give us a divide by 0 error, right, for the Q score. Okay, yeah, let's just do that. Let's fix that. TS. I'm glad I caught that. Right here. Return this dot Q score. No, this dot num visits equals to 0. Then just return 0, or else that. So if like, that'll fix the divide by zero. If that equals 0, then we just return 0 as the score default draw. Like, we don't really know much more about it because we've never visited it. Or else we return the num visits. So it's never been visited before. We treat it as like 0. Like, we just create it like, because like when we create the node, we know the value, like our estimate for like this node, but then we've never actually like told our model to like, we've never actually like, if this is like the next state, we've actually never like gotten a value for this yet. So like we might as well set it to 0. Like, like yeah, initially we just kind of initialize it to 0. Okay, that looks good. What? Okay, redo. Okay, let's save that and quit it. Or wait, yeah, save it and quit it. So the number is 0, then we return 0, or else we do that. We just like take score sum divide by that. And then let's say it's not 0. Like, let's just say the number is 1 and the edge, right? Let's say that we take the edge and then like, okay, so like we're taking the edge, we're taking this edge, which is for 0, and then we kind of create the next state, and then num visits is 1, and then q score sum is whatever that is. So like, okay, good, yeah, that works. Okay, I get it. Clear, make sure it runs. Good. Get status, clear, and get diff. We already talked about this. Talked about all that. Talked about q score sum, running total. And then this thing right here. So if it's 0, we return 0, or else we just do the average. Good. Now here's like the actual highlight. Again, I've talked about this quite a bit. Terminal, okay, easy check. Then we iterate over the edges. We select the best one with like the highest UCB score, tie break randomly. Then we need to like know what to bubble up, because like that's kind of like the goal, to bubble that up. Now there's two cases. Either like we can just simply recurse, or if it doesn't exist, we've never actually traversed this edge, then like you need to like look at, we have to create a new node in our graph, right? To create a new node in our graph, like we actually create the node, and then like creating the node not only like creates the node, but also like kind of gives us the value and like the policy. The policy is kind of embedded inside this node. Like if you look at create node, which is right here, then the new node takes in the edges, and the edges kind of have the policy in them. Like each edge is in fact the move in the probability, which is sourced from the moves and probabilities, which is sourced from the policy. And that, of course, is kind of, we get that by invoking the model and like doing the policy and value prediction, which is done in the net.ts class, which the game also uses. Like we know it works, I believe. And of course, this create node also, like, that's where it defines the terminal cases too, that we're so nicely using right here. I mean, right there. It's kind of like applied here in create node. So anyway, so back to this one. We've never taken this edge, so then we just like, we just advance, like, we've never actually taken the action before. Then we actually like apply it. We copy the game state, it has to be a new thing. We apply it, and then we kind of use that in the net. We have to apply the net. Like rather than doing a Monte Carlo tree search, here's where we do a rollout. Like we actually perform a rollout here by doing a bunch of random actions until we get a terminal state and propagate that up. Instead, we just like use a neural network. Like that's the whole point of AlphaZero. And then we kind of, so we create a new node which has the policy embedded in the edges, and then we have like the estimate that the network gives us for the value, which we propagate up. Either we do it recursively, or we like just do it for the first time. kind of similar to like kind of calling this once and then boom, we just kind of like sorry, we call this once and then like that. It's like this is I already talked about that. And then Q score sum, yeah, we're just kind of adding it to our like running total. Like yeah, we're just kind of adding that there. And then we're kind of doing the bookwork for non-wizards, like we're incrementing for the edge. And whenever we do this, we have to also do it for the parent node that the edge is attached to, like the child of. And then we have to stick a -1 here. Just like how in create node, we do -1 times value. Because remember, all these values, right, are from the perspective of the game state, like whose turn it is. Like the node's state's player, like the perspective for the node's player. But we have to do -1 so that like when we actually like recursively call it, then like the -1 kind of flips it to be the correct perspective that we care about. So like we can properly use the contribution, like in like kind of handle it, take care of it at our level, and then yeah, that's the whole point -1. Okay, that looks good. Create node, yes, this is terminal case, and then like we just kind of yeah, I just talked about that. And then this thing I just kind of randomly felt I just felt like doing instead of like eliminating a possibility. Actually, I don't know. There's something called temperature or like some noise Dirichlet. I don't know. Like there's like actually okay. I'll have to think about this later, but I don't know. Like, what if the network says to like never make a move, but like we might. Hmm. Well, I guess MCTS might just like say, hey, like we've explored a bunch of different moves, so like let's just like the whole exploration term, like we've explored a bunch of moves, but we haven't explored this one. So then, like the one we haven't explored would have like a high right hand term, right? Like the square root of the total divided by like that action would have low denominator, so high value. Okay, I guess I'm comfortable removing that, and then to guard against the divide by zero, like that's just kind of this one. We could just like copy and paste it as is if it's like greater than zero. Like we can divide by it if it's not equal to zero, but if it is equal to zero, then let's just kind of like do a uniform. Again, I don't expect this to like. I don't think this is a very common occurrence, but yeah, that I really doubt that this else case would ever be hit. But if in case it does, then we just like defend against error, zero error. Like this felt pretty kind of. This did not feel like a nice way to defend against that. Like avoid divide by zero. If some probably, I think that this is better. Just do it like just divide by uniform. Uniform like same probability for every single thing in case they're all zero, and that's it. Get status. Huge commit. Clear. Get status. Get get log. Get commit. Uh, initial tentative completion of MCTS search untested. Get status. Get push. And it compiles, which is nice. Get status. Get pull. Okay, commits. Last thing was from last week. Refresh. Now, 102 additions. Some good stuff. Some good looking stuff. Exactly. That's why the whole negative sign is from. Should know it exists. Exactly. Like that's why rather than do it in here, we kind of like do it in here. This whole yeah. This case node doesn't exist, so we make it exist and we return the value. There. Kind of reminds you of like how like sometimes in depth first search or like in breadth first search, like you have the fringe, which can be like a stack or a queue, let's just say a queue. Then like if you're searching for a goal in like let's say breadth first search, like we kind of like do it like we have a queue, like we take all the things, like we're searching for a goal node, like we kind of we like one approach is like you pop it off the queue and then if it's terminal we return it if it's the goal. But then like another approach, which I guess like this kind of takes, is like before we like take the node, we expand out all its children, add them to the queue. Like we find out that we already found the goal we're looking for, we just return it, as opposed to like taking all the children and queuing them, and then when it's their turn to come off the queue, we just like say, hey, we found it and we're done. Rather than that, like before we put it on the queue, we can like do the check right there. I feel like it's kind of like a 1.5, like, and rather than two iterations, we did 1.5 iterations, or like it's like an off by one thing. It's not a big deal. Like we could have done something similar, like this. In fact, maybe that's even better. But I don't know. I'm just when I'm doing tree problems, I tend to like preconditions of searching never be null. That's like a nice like a non-null precondition, which I guess that's just like a personal taste issue there. So yeah, no big deal. It's okay. And then the bookkeeping, all the bookkeeping right here, and then -1. And again, also -1 for like this case right here. Oh wait, no. No, wait, no. Value contribution is negated, but in create node, we're also negating it. Wait, no, that's wrong. Wait, hold on. No, I think that's fine. So like create node, so it's the next game state, right? It is the next game state. Okay, let's say that this edge to take is really good for us. Let's say we're player one. It's really good for P1. It's great. That means next game state dot apply move. So now it's P2's turn. And from P2's perspective, the network, let's say it's a very good network. Let's say it's -1. It's really bad for them because it's very good for us. It's very bad for them. -1, let's say, or -0.9, 0.99. So let's say this edge to take is really good for us. It puts us in a state where we're 0.99. Then for them, create node would say like, hey, you're in a -0.99. Like that's how much this value would be -0.99, and then we invert it. Sure. Wait. Well, let me take it from the top. Edge to take puts us in a state like that we're 0.99. It's really good for us. That means from P2's perspective, it would be this value that net would return is -0.99, so it's really bad for them, P2. But then we negate it because that means it's really good for us. So then negation of -0.99 is 0.99. So then like that is really good for us. Like we factor it in. Yes, and then we negate it to propagate it. Yeah, okay. That's so then like just how create node does a negation at the end of it. Yeah, exactly. Like just how this at the very end return does a negation. Then just like how at our very end, like in the search at the end is a negation. So like that's completely fine. So like this negation and the negation at the end of that negation, they both flip it to our perspective so that we can use the value contribution. And then, now that we used it, we bubble it up, we respectfully negate it so that the person who invoked us from like its other perspective can properly take it into account. And then kind of similar to that negation right there. Terminal value, again, when we're setting it, is always like in the perspective of like terminal value, like I mean, like yes, we could like swap and like kind of build in the negation, but I think the terminal value should be from the perspective of the game state. So like in this case, if it's a player 1-1 and it is its turn, then great, like they line up. And then obviously you flip it for the other one. So yeah, I think that's good. I think that's all. And then okay. And then because like we kind of extract this from the comments, right? Like somewhere we'll have to delete that too. Yep, right there we're deleting that. Just like how like, yeah. Yep, and okay, I think that's a lot of work, but I feel that like even if it's not fully correct, there might be some bugs. Overall, I think like the whole idea, in general, I think that like this is a good idea. And then the remaining work is to actually like call this, like the whole, like this whole init stuff right there, or like this thing right here, initialize search tree. Like the whole idea behind that is like, I already talked about this last time. Like now the whole thing, like we've been like kind of gradually like uncommenting stuff at the end, right? Like we had a bunch of stuff. Like we took this whole create node, which was first in our comments, our multi-line comment, and we kind of like brought it out. Now, like once we're done, like the final thing to do is to like kind of take this and uncomment it and actually like use the search, right? Like we have like this number here, like number of Monte Carlo tree search simulations, and then actually, wait, 1800 is too much. Wait, no, hold on. How did I get this number? I did like 42. Yeah, wait, it's right here in the year 42 squared. No, it should just be 7 squared, right? Like 7 columns. It should be 7 squared. Yeah, just 7 squared. Because like player 1 can like put 7 columns, and for each of those columns, 7 more columns. Yeah, 7 squared. Forty-nine. 49 is around like 50. And let's double 50 to 100. Want to at least be 7 squared, since P1 can. Well, actually, let's stop. Since P1, oh, well, whatever. I'll set this to 100 without any commentary. I actually saw some comment like somewhere here, like the number. I know I saw the original author mention square. Like, I remember like he kind of talked about like how to come up with this number. Something kind of intuitive that I thought too. Uh, yeah, exactly. I'd also take average branch factor into account and keep the number of simulations at least as including depth to search. Exactly. Like if I can make 7, they can make 7. So that's kind of like how that's kind of how. And I don't know anything about temperature to be honest either. But yeah, that's just like anyways. So yeah, just squared. So like I did 42 squared because like 42 is how many kind of squares they are. Like 6 here and 7 there. But the actual moves are just 7 squares like that. And then 7 squared is 49, which is so close to 50, a nice round number. Let's just double it to hundreds. Hundreds a nice round. The roundest of all numbers. Like a very round number in decimal. Okay, yeah, that's good. Clear. Get status. Get diff. 100. Okay, yeah. I think that's sufficient. I think I'll stop now. I'm pretty, yeah, I need to eat some food. Exit. Or, yeah, just quit. Whatever, I'm done. All that's left is to actually, use this. Like this whole comment, like we're gradually taking stuff in the comments and then bringing them out. So it's finally, it creates the root. Like the whole point, ultimately, is to take a game state and a model and give a refined policy. Like we could just invoke the model and get a policy, but then we do the search a whole bunch of times, specifically 100 times in our case now, because 1800 is way too much. And by doing it, the more times we do it, like again, we get a more refined, improved Monte Carlo, improved policy for policy improvement. We got the we got the improved policy, and then like from the root and the edge cases get an improved policy, and we return this policy, and then like when we're doing self-training, we randomly sample from that policy according to like we sample from it, and then we get that. We get like which moves to play, and then like we self-play with our improved policies, and then we get training data. We pass that in, and then we get an improved network, and then we keep doing it again and again. It keeps getting better, and we're done. That's that's all. Yeah, that's good stuff.